To begin the reverse engineering process, I first disassembled the TTDC gear motor in order to observe the internal components and understand how the system works. The first step is removing the plastic cover off the gearbox. The cover protects the internal gears and the motor from sliding out and aligning them for operation. After removing the cover screws, the gearbox casing can be opened. Once the casing is open, the internal gear train becomes visible. The motor uses multiple plastic compound gears arranged in a proper sequence. These gears are stacked on small shafts inside the gearbox and meshed together to transmit motion. After removing the gears, we can see that they are different sizes in diameter, and the DC motor itself can actually be taken out the housing before even unscrewing the gearbox. The motor shaft connects directly to the first gear in the gearbox, which begins the gear reduction process. To reassemble the motor, the gears are first placed back into their original position inside the gearbox housing. Each compound gear is aligned with the other so that the teeth mesh correctly. Next, the DC motor is inserted back into the gearbox so the motor shaft connects to the first gear in the train. After that, the gearbox casing is closed and secured using the screws. And finally, the plastic cover is placed back on top of the motor to hold the assembly together. The TTDC motor is a small electrical motor that converts electrical energy into rotational mechanical motion. When voltage is applied to the motor terminals, current flows through the copper winding inside the motor. These windings create a small magnetic field that interact with permanent magnets inside the motor casing, causing the rotor to spin. The rotor is connected to steel shaft, which transfers the rotational into the gearbox. Inside the gearbox are multiple plastic gears that reduce the rotational speed of the motor while increasing torque. This gear reduction allows the motor to have heavier loads such as wheels. The gearbox housing and gears are made up of injection molded plastic, which keeps the motor lightweight and inexpensive to manufacture. The final gear transfer the torque to the output shaft, which can be connected to external mechanical components such as wheels or other mechanisms. And then this motor is an important component since it acts as a primary actuator that produces motion. Without the motor, the system would not be able to generate rotational movement. The TTDC motor operates using a combination of electrical and mechanical systems. The electrical energy is first converted into magnetic force inside the motor. The force causes the rotor to spin, which generates mechanical rotation. This rotation is then transferred to the gearbox, where the gear train reduces the speed while increasing the torque. This design allows for the motor to generate enough force to drive loads such as wheels. The design of the motor also influences the performance, reliability, and efficiency. The internal gear reduction improves performance by increasing torque at the output shaft. The use of injection molded plastic gear causes and casing helps keep the motor lightweight and inexpensive to manufacture. However, the plastic gears may wear over time with extended use. The compact gearbox design can also improve efficiency because it allows the rotational motion from the motor shaft to be transferred to the output shaft with small space. Although some energy is lost due to friction between the gears, these losses are generally small and do not significantly affect the overall performance of the motor. Overall, the TTDC motor demonstrates how electrical and mechanical systems can be combined in a simple and low-cost design to produce useful mechanical motion. And here's the labeled breakdown of the assembly and reassembly of the